Okay, so we're going to do the second part, or at least part two, of our Unit 1 notes, Introduction to Chemistry. This is going to start the math and chemistry portion as we talk about it for this unit. Mostly what we're going to be discussing when we talk about an introduction into the math and chemistry will be basic math problems. So this includes basic math concepts such as accuracy and precision, percent error, significant figures, our metric system, dimensional analysis, and density. So let's first talk about accuracy and precision. So accuracy refers to how close individual measurements agree with the correct or true value. So essentially what your given value is, what the expected value is. Anything that is basically told to you would be considered the correct or true value. So if you're expecting to get, if your ruler is supposed to be 30.6 centimeters, then you should get your answer to be 30.6 centimeters. Okay, precision, on the other hand, is a measure of how close the individual measurements agree with one another. So essentially, you can be precise and not be accurate because you can be really close, but instead of getting that 30.6 that you're looking for, you could get 25.1, 25.2, 25.3. You would be precise because you're really close in all of your measurements, but you're not accurate because you're nowhere near where you're supposed to be. So when we look at accuracy and precision, accuracy tells how close we are to our correct value, whereas precision tells us how closely those measurements are to one another. So when we look at these little dartboards, I like to use the example, I am terrible at playing the game of darts. So while I will probably never be number 3. Instead, I will be 1 or 2. I can guarantee you that when I am playing darts and I've had some adult beverages, I will probably hit the same spot over and over again and it not be the correct area. So I have, when I've had some adult beverages, some great precision. Okay, so my measurements here, or my darts, are precise because I'm hitting the same spot every single time, not where I'm supposed to be hitting it. I probably have a score of like 3, but I'm hitting the same spot every single time. Now, when I look at, we'll get back to these in a minute. Now, when I look at these are played by somebody who is much better than me because they are able to consistently hit the bullseye. So they are both accurate and precise. So that would be one that is what we call the gold standard, or what we should get. If you are working in any field, you want to make sure, any field of science, you want to be sure that you're accurate and precise. This is your ultimate goal. You want to make sure that you are hitting that bullseye every single time because it could be someone's life on the line. Or in our case, someone's dog's or cat's life is on the line. Now, when we look at these, at first, you probably think that these are neither accurate nor precise. However, it's not accurate, it's not precise because of how they are spaced further from here. They could be considered somewhat accurate. Because they're almost exactly apart from the bullseye. So let's actually look at this as we apply to data. So the first one, when we look at this, we're going to put a plus if they are accurate, minus if they are precise, and neither we're just going to leave blank or write neither. Okay. So Nikki here, she's really good. She's supposed to get 30.6 inches for her result. And when she takes her measurement, she gets 30.6, 30.5, 30.4, and 30.2 centimeters. So she is both accurate and precise. Sam, on the other hand, gets 27.5, 27.6, 27.8, and 27.4. So while he's not near the 30.6 centimeters, he is precise because he's hitting all of these on the bullseye in the outer area. Now, Chris is kind of like me. He's a little bit all over the place. But when we look at this, he gets one that's 30.6, one that's 31.5, one that's 32.6, and one that's 25.8. So while they're a little bit further from accuracy than Nikki, he is accurate. He's just not very precise. And Jason, unfortunately, Jason's not very good at taking measurements. And he is neither accurate nor precise because his 27.6, 24.1, 25.6, and 23.1 is not precise because they're not very close to each other. And he's not close to the expected value of 30.6. So, what happens if you're like Jason? And what happens if a person who's working in the chemistry field or any other science field is like Jason's? Well, he experiences a great amount of error. And essentially what error is that is the difference between the measured value and the accepted value, or correct value, or true value, or given value, whatever the value that you're given that is supposed to be the standard. So if we were looking at 30.6, the accepted value is 30.6. Okay. So what are the types of errors that we can see? Well, the first one is going to be systematic error. So in systematic error, this occurs in probably the case of Sam. And it occurs when we have repeated errors due to faulty equipment. So in Sam's case, he might have been using a roller that was not properly, didn't go through the proper quality controls. And when that ruler came out, it was actually 3 centimeters shorter than what it should have been. And measuring 3 centimeters shorter than what it should have. And so therefore, his root cause could probably be identified. So he can state, oh, this ruler that I'm using to measure my 12-inch ruler is terrible. So I need to go and find another ruler, and then he'll probably get the correct answer. Or the 12-inch ruler was made short and he realizes his sample is incorrect. And that means that he actually needs to look at, look at, what's going on with the system. But generally, it can be determined that there's a root cause that we can find easily. The second type is going to be human error. Okay. And this, okay, is the most common type of error. So how is this error, how is this defined? It's just errors made by the scientist or veterinary technician. And this can invalidate the data. The nice thing about this is that the root cause can be identified. And it may be annoying because you have to repeat something or do something over again, but it does allow for you to have the opportunity to fix the wrongs that were made and be able to fix the problems that were occurred and you know, redo the experiment. Yeah, no one likes to do any experiment twice, but this is a common type of error. It happens and it's easily fixable. Systematic error, you typically have to do multiple times and then you got to do it all over again. So systematic error, in my opinion, is even more annoying than human error. The last one is random error. Okay, and what does this kind of tell us? These are errors that have no identifiable pattern. So we really don't know exactly why they happen. They just kind of do. And sometimes it like has to do with the environment and, you know, even changing the environment. Like it's just, unfortunately, it happens. So these are completely random. They're not very common. So most people can usually identify a root cause to their errors. These are not very common, so you typically don't see this. If you do, you're just frustrated because there's no reason for that error to have occurred. And as scientists and as, you know, students of veterinary technician, you guys have somewhat of an interest in science to an extent. So you don't want to not know why something's happening. You want to be able to figure it out. So random errors are not very common. When they do happen, they tend to frustrate all the scientists. Okay, so let's look at these two following scenarios and determine whether it's systematic, random, or human error. So Brandon spilled his sample when transferring it to a graduated cylinder for measuring. So this would be considered human error. And that's because Brandon himself spilled it. So he could have taken a measurement, or if he was smart, he just stopped what he was doing right there, you know, wrote sample was spilled upon transfer, and then redid the experiment without actually having to completely invalidate all of his data. The next one, Carla consistently measures a teddy bear 2 inches longer than the accepted value. So that would be a systematic error. It could also possibly be a human error, but the idea behind this is that her ruler is not it was not made correctly, and so therefore she's measuring it 2 inches longer because it's, or the teddy bear is made incorrectly, but there's a root cause that it's not the scientist. Now it could be that she just doesn't know how to use a ruler and is measuring 2 inches incorrectly because she doesn't know how to use a ruler. That is a possibility as well, in which case that would be considered human error. So when looking at error, we need to look at percent error. And essentially when we look at percent error, we're just trying to give a number to the difference between the measured and accepted value. So we're looking to not only define what that error is, but also give it a percentage, or essentially like how bad is that error. So let's look at this. We have percent error is equal to the actual, whatever that is. That could be accepted, given, whatever it's called. That's the actual value. So the number that's usually given to you in the question minus experimental. And we take the absolute value of both of those. That means it always should be positive and divide it by actual. Then we multiply this by 100. So when looking at Nikki's, we're going to take, before we can actually do any of these, we need to take an average and then use that average to determine our percent error. So we have 30, 30.5, 30.4, 30.2. If you average those together, you're going to take 30.6 and I'm going to get my calculator out for you. So you're going to take your calculator and you're going to go 30.6 plus 30.5 plus 30.4 plus 30.2. Okay, so it gives you 121.7, and we're going to divide that by 4. So we get 30.425 cm, which we're just going to do to the first decimal place for the rest of these. We'll explain in a little bit why we do that. But for right now, just leave that as is. So we're going to take 30.4, and our accepted value is 30.6. So we're doing our actual, which is 30.6, minus our experimental, which we found to be 30.4, and then divide that by 30.6. And then we're going to multiply by 100. So we get 0.0654%. Okay, because I'm rounding off, we'll say to 3, what we call sig figs. So we have 1, 2, 3. We'll talk about what sig figs are in a minute. So just do it to the 3. You have 3 whole numbers. Okay, Sam. So Sam, we're going to look at, we're going to put in 27.5 plus 27.6 plus 27.8 plus 27.4. And then we're going to divide by 4. And so we're going to do 27.6 as our average. So now we're going to take, using our percent error, we have 30.6 minus 27.6, all divided by 30.6 times 100. So our answer should be rounded off to 9.80. Chris, we're going to take, and he's got 30.6 plus 31.5 plus 32.6 plus 28.5. Then we're going to divide that by 4. So we get 30.8 for our answer. So we're going to take 30.6 minus 30.8. Look, we get a negative, but remember, what are we using? Absolute value. So we're going to negate that answer. So we should get 0.2 divided by 30.6 and then multiply that by 100. We should get the same answer that we got, which is for Nikki, which is 0.654. And the last one, we have 27.6 plus 24.1 plus 25.6 plus 23.1. And then we're going to divide that by 4. So we get 25.1 centimeters. So we're going to take 30.6 minus 25.1, all divided by 30.6, and then multiply that by 100. So we should get 18.0% error. So who is the most accurate? Well, technically, it is Nikki and Chris because they both have the same percent error. However, Nikki is better because she was also precise. So whose data is the best would be Nikki's. However, Chris is still acceptable because his percent error is very low. While he's all over the place, his percent error is low, so we would still accept that data because it is accurate. The better data, and the data that everybody wants to reach towards, is Nikki's data. So why did I round off to those specific numbers a minute ago? I said, remember, don't worry about that right now. We're going to talk about it in a minute. Well, that minute is here. That minute is going to be about significant figures. So when we look at significant figures, every single number that we ever take in this class will have a certain amount of what we call uncertainty. So that uncertainty is essentially meaning that we're always going to be guessing one uncertain digit for every single number that we take. Reasons why we do this is because depending on the precision of our measuring tool, we could have a lot of uncertainty or a little bit of uncertainty. And we also want to look and essentially take out as much as we can of the individual using the measuring tool. So when we look at this, whenever we take any type of information, whenever we decide to take any measurements, we're looking at every number of every number is going to consist of all certain digits and one uncertain digit. So when we look at this graduated cylinder, we can determine what our graduation is, which that plus our numbers will be our plus these numbers will be our certain digits. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 hashtags or 10 slashes in between 1 and 2. So if you take 10, okay, if you take 1 and divide it by 10, you should get 0.1. So every single hashtag is going to be 0.1. So if we look at this, we have 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. So my known are going to be my 2.6. That's going to be the known digits or certain digits. Okay, those are my certain digits. Now, in between my two digits, I'm just going to take a guess, and that's my uncertain digit. So this 4 is my uncertain digit. And that's the one that I've guessed. Now, you could have thought and looked at that graduated cylinder and said to yourself, wow, I think that's 2.65 or 2.65 milliliters. And that would have also been a acceptable answer. You could have also chosen to say, well, it's 2.66. That's also an acceptable answer. Again, you're looking at how close the graduated that line is to whatever, and as long as it's within that reasonable range, that is an acceptable answer. I wouldn't say that this is 2.61 or 2.69 because it clearly is in the middle, halfway in betweenish, between 2.6 and 2.7. So let's go ahead and practice. Tell me which of these is a digit of uncertainty. So it's always just going to be your last digit. That's kind of the easy way to remember this. So your last digit is the 9 there. Here, our 2 is actually our digit of uncertainty. We have a 6, 4, 8, and 4. 6, 3, 8, and 4. All of those are the last digits, and those are your digits of uncertainty. Now, here's a little trick for you. Well, how does this really apply to you? When you look at your thermometer is going to have a specific last digit, right? Well, that's your digit because you are taking a measurement. You're taking your temperature. That measurement on the thermometer, that last digit is typically an estimated digit or a guess based off of what the computer is allowed to read. So when you look at what allowed to read off of you, if you do a forehead thermometer or if you do any other type of thermometer, the last digit is going to be the digit of uncertainty. So there's really not a whole lot of difference between 101.4 and 101.5 or 100.4 and 100.3. It is all just a guesstimation. So if you wanted to, you could reason with your doctor saying that you should go get tested for COVID if you had a temperature of 100.3, because remember, it could easily be 100.4. A little hint for you in the future. So this whole idea of every number consists of all digits you know and one you don't. So what you know plus one, what you know plus one you don't. Okay, that's considered what the definition is for significant figures. That's the number recorded in a measurement that includes all certain digits plus one uncertain digit. So this is where we get to the fun part of the rules of significant figures. And this is where you're going to start hating zeros, because zeros are the most confusing part of this. I want you to really remember what I said to you in here. It consists of one uncertain digit. So let's say that my line actually went, and you do not need to write this on there, went to here. So my line, the meniscus, which is where I read from, went straight over exactly 2.6. So if it did that, I would still have to write 2.60 because these are my known digits, right? And my 0 would be my unknown. So with that being said, the first rule of significant figures is that non-zero digits are always significant. So all non-zero digits are significant. Okay. Any zeros in between numbers, so any zeros in between non-zero digits, are significant. So that means they're counted. Anytime I see the word significant, that means they're counted. For our total number of sig figs. Zeros that are at the end of the value without a decimal point are not significant. Essentially what's happening there is that they're acting as placeholders to let you know that we need to go to the tens place, or that we've gone to the hundreds place, or the thousands place, and that our digit of some uncertainty is in the hundreds or thousands or tenths or tens or whatever the case may be place. It's not in the ones place. If there are zeros at the beginning of a value, they are not significant. So all of these zeros here, again, are just acting like the zeros at the end of the value without a decimal point. They're acting as placeholders. They're essentially telling you that you start on the thousands place, or you start on the 10,000s place, or you start on the hundredths place. You don't start on the tens place. That's all they're doing. And the zero in front of the value, the zero in front of that decimal point, that's used to indicate that there is a decimal point there. We will always write 0.00, whatever the case may be, 0 point something, because it's very hard to read, especially if you're like looking at like a vet's information. If they don't put 0.0 blah 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 blah, or 0.5 and 0.5, or you put 0.5 and 5, and you don't see the decimal place, you can easily give the wrong amount of medication. So as a general rule for science, we typically put the zero in front of the decimal point in order to indicate that it's less than 1, because 0.5 and 5 are very different numbers and can be detrimental to that dog's, or cat's, or whatever the case may be, system. The last rule is that zeros at the end of a value with a decimal place are significant. So let's do a little practice here. So how many significant digits are in 4.0034 centimeters? Well, the only rule for zeros that apply here is the rule number 2. Zeros in between non-zero digits are significant. So we have 1, 2, 3, 4, 5. Because remember, these zeros are found in between non-zero numbers. So we have 5 significant digits in that number. Here, our significant digits are 0.0, we have significant digits in the number 0.0025 milliliters. Well, this follows rule number 4. Zeros at the beginning of the value are not significant. So we only count the 2 and the 5, and that gives us 2. So let's do a little more practice just to make sure we're all 100% on determining the number of significant figures. If you have questions on this, please feel free to contact me. I am more than willing to discuss a little bit more about significant digits. So the first one here, this follows rule number 2. And with rule number 2, any zeros in between non-zero digits are significant. So we should have a total number of 5 significant figures. Here, zeros at the end of the value with a decimal point are significant. So we'd be following rule number 5, and therefore this 0 is significant, so we count it. So we have 1, 2 significant figures. The next one, we follow rule number 4. Zeros at the beginning of the value are not significant. So we're not going to count these zeros because they're not significant. We're only going to count 4 and 5, which should give us 2. Here, our 0 is in between non-zero digits, so we do count it. So we have 1, 2, 3, 4, 5, 6. This one is easy. There's no zeros, and all non-zero digits are always significant. So we have 1, 2, and 3. Here, we're following rule number 4 again. So we don't count any of these zeros, and we start with the 3. We have 1, 2, and 3 significant figures. The next couple should be pretty easy. They only have non-zero numbers, so they all are counted. So as you can see, we have 3, 2, 4, and 3. The last one here, 2.90 kilograms. Well, zeros at the end of a value with a decimal place are significant. So we will count that 0, and it gives us an answer of 3. Okay, the following one, there are only 2 because zeros at the beginning of a value are not significant. So you should have 2 significant figures there. So that's how we use significant figures rules. Again, the idea that really helps you understand these rules is to remember we're only counting all the known digits plus one uncertain digit. So this is not really known digits. There's just placeholders to indicate that we are starting at a much lower and a higher precision instrument or tool. Okay, so let's go over just the basics of the measurement of the metric system. Again, this is really going to be quite quick in my opinion. What you need to know for this class, and these are just the base units that I want you to use from the metric system and what we'll use and see maybe in some of the online labs you do this semester. So the first one is going to be mass is always going to be measured in grams. Always just going to be measured in grams. Your mass in grams won't change depending on whether you're in orbit or whatever the case may be. You will be the same no matter where you are. The volume is going to be measured in liters. So if you ever had a 2-liter soda, that's what we're going to be looking at. We're looking at liters. Length is going to be measured in meters, which we're not going to be super concerned with. We will see, a little bit about that, but for the most part, we're going to be dealing with mass and volume. We're not going to see a whole lot of length. We will see some seconds. Okay, and this is similar to the English system. We really didn't change up our time from what the metric system was. That didn't really change very much. The nice thing about these first three is that we can use good prefixes for them. We have Kelvin, or K. So we will be, Kelvin's not really measured per se because typically we get very high numbers with it. Typically you've either heard of Celsius or Fahrenheit, but for most of the calculations you're going to need to do, you're going to need to know what Kelvin is and how to use Kelvin when we use temperature. Because most of anything that we're dealing with temperature and changing the temperature of something, we're usually dealing with Kelvin. We won't talk about gases and how those work because it doesn't really apply to you as super much, but all gases are calculated in Kelvin. The last one is going to be the amount of substance, which is mole. We will talk about what that mole is and how we calculate for it when we get into chemical reactions because it plays a huge role in not only balancing, but also in stoichiometry. Okay, so when we look at these prefixes, we're only looking at it for the first 3, grams, liters, and meters. And sometimes you might hear of like milliseconds, but they're not very common and we won't be using it that much. We won't use the prefixes that way for that. So let's just keep it simple and let's use grams, liters, and meters. So we can have a lowercase k, because remember an uppercase K is Kelvin. This stands for kilo. And essentially that's 10 to the third, or 1,000 grams goes into a kilogram. If you've been to your doctor's office, if you go to Penn State recently, I believe LGH still does pounds and then converts to kilograms. But I know at Penn State, they only measure you in kilograms. So a lot of people are actually phasing out pounds in order to align more with the rest of the world that measures their weight in kilograms. The next one is going to be H or hecto. And this is 10 to the 2. What that means is that, let's say we have a hectometer. We have 100 meters in that hectometer. It's not very common. You probably won't see it a whole lot. You'll see kilo most out of these three, but it's important that we talk about all of them. DA stands for deca, and that's 10 to the first, or 10. So a decameter would have 10 meters in it. Then we get to our base unit. The next one over is going to just be a plain D, and that's deci, or 10 to the minus 1. So it means, just like we said with 10 to the plus 1, we had 10 meters in here. When we look at this now, we're going to look as meters as our unit, and we're going to see that we have 10 decimeters in a meter. C stands for centi, and that's 10 to the minus 2. So what does that mean? We have 100 centimeters in a meter. And the final one is milli, which is 10 to the minus 3. And what that means is that we have 1,000 millimeters in a meter. We have also a bunch of other types of prefixes that you have been given in your note packets. The ones I gave you were just the first 3, but some other ones that would be good for you to know would include, have anybody heard of gigabytes? Gigabytes. We also have like kilo, mega, nanometers, micrometers. So again, the ones that you would be good to know are obviously going to be giga and mega. You could even have a terabyte of data. The other ones that you can know would be micro, because you've heard of micrometers maybe, nanometers, when we talk about, if you've ever talked about wavelength, and pico. Okay, so we have what we call standard units, standard international units, and metric units. So not everybody uses the exact metric system anymore. And it's really similar. Most of the time, the metric units are going to be pretty much the same. The only difference is, for instance, we have kilograms for the SI units. We'll use meters cubed or cubic meters. For volume, length will be the same with a meter. And time will be the same because time is the same for everything at seconds. Temperature will be the same with Kelvin. Our moles will be the same. And what I don't really talk about that much is ampere. We're not going to deal with electrical current that much. I don't think that that's something that you super need to be able to know. And luminosity is not something you need to know. Just realize that this kind of goes with the whole list. And if I don't tell you one on the list, I have to tell you all on the list. So what kind of like comparing them, what is different is we have grams over here, which is just G, and liters for L. The same is going to be the meter, seconds, Kelvin, and our mole. What's going to be different is if the SI is that you're going to use meters cubed, kilogram, ampere, because they don't really use much determination of electrical current, and candela. So those are really the difference. That is all we're going to talk about with the metric system. What you need to know is that grams, liters, and meters. And then we'll eventually talk about moles, but for right now, it's not super important. And we will talk about seconds. Again, right now, that is not the most important thing for you to know. I will also give you for what you need to do for the rest of this for dimensional analysis for this class. I will also give you in your notebook, you should see that there is a common conversion factors found. So you have those so you know exactly what you need to know for that. Okay. So let's start talking about dimensional analysis. That was the whole reason we kind of started talking about metric system and prefixes. Well, dimensional analysis itself is a problem-solving method that uses the identity property for math. And the idea is that identity property says that any number or expression can be multiplied by 1 without changing its value. So essentially what we're saying is that if 1 foot is equal to 12 inches, that's the same thing as saying 1. We're kind of doing the same thing you would have done with the identity property in math with fractions, but instead we're using conversion factors as our fractions. So some examples would be 1 foot is equal to 12 inches. 1 minute is equal to 60 seconds. 1 hour is equal to 60 minutes. 1 meter is going to equal 1,000 millimeters. And 1 kilometer is equal to 1,000 meters. So how do you solve these? Again, conversion factors mostly provide a bridge between the metric system and the customary system, which is what we use, or the English system. So how do you do this? You're going to write down your units and then draw your grid. Now, for all of these in here, except when we get to the end, I have drawn the grid for you. You put your given units on the bottom. You need to look where you need to go and put those units on the tops, and then you can add in the correct number based off of your conversion factors with those units. So let's do an example. We have our conversion factors right here. So if we need them, we know where to look for them. So we want to convert 1,245 seconds to minutes. So we're going to convert 1,245 seconds to 60 seconds is equal to 1 minute. Okay, because we're going from seconds to minutes. And if we remember, I said 1 minute is equal to 60 seconds. So when we calculate that, we're going to take 1,245 times 1, and then we're going to divide that answer by 60 because we multiply across the top, multiply across the bottom, and then divide the top by the bottom. So we should get 20.75 minutes. And here's the thing, I had 4 significant figures to start with. I don't count how many sig figs I have in my conversion factor because it's just multiplying by 1. So I should have 4 significant figures in my answer. So I have 1, 2, 3, 4, 1, 2, 3, 4. Okay, let's do some 2-step conversions. So we want to go from seconds to hours. So we have 3,056 seconds. And we want to go from seconds, and then we're going to put hours on the top here. Now you can find something that would probably give you exactly how many seconds go into an hour. However, based off of my conversion factors that I have in your notes, I don't have that. So I need to find something that's what I call the in-between number, or the in-between unit, which is given to me here. I go from 60 seconds to a minute, and then I can go from minutes to hours. So I'm going to put in minutes and minutes. And then I put in my numbers. Because remember, it was 60 seconds per 1 minute, and then 60 minutes per 1 hour. 60 seconds per 1 minute, 60 seconds per 1 hour. So now I'm going to multiply across the top, multiply across the bottom, and then divide the top by the bottom. So I should get 3056 times 1 times 1. That's the same. Take 60 times 60. That should get me 3,600. So I take 3056 divided by 3,600. Should give me 0.8. And remember, I need to go to 4 significant figures. So I have 1, 2, 3, 4. I need to look to the right and then round up because it's between 5 and 9. Okay, final one we're going to do is going to be advanced dimensional analysis conversions. And this is where you're given going from kilometers per hour to from miles per hour to kilometers per minute. So this is going to be a little bit more complicated. So how do I write my first one down? I'm going to write 65 miles per 1 hour, because that's what it says, per hour. That's saying per 1 hour. So I want to go from miles to kilometers on the top. But here's a little different. I want minutes on the bottom. So I need to put my hours on the top and my minutes on the bottom. So if I look at what my conversion factors, I should have them for both of these. So let's find one. I have 0.261 miles per 1 kilometer. So I'm going to put 0.6261 miles per 1 kilometer. And I already know that I have 1 hour is equal to 60 minutes. So I'm going to multiply across the top, multiply across the bottom, and then take the top and divide it by the bottom. So we have 65 times 1 times 1. That gives us 65. We take 0.621 times 60 times 1. So I get 37.26. So I'm going to take this 65 and divide it by 37.26. And how many sig figs did I start with? 1, 2. So I can only have 2 significant figures in my answer. So I have 1.7 kilometers per minute. Okay. Now we might have some situational conversions, in which case I may not be able to give you the exact answer or the exact grid, because it depends on how you approach the situational conversion. So your car gets 21 miles per gallon and your friend's car gets 14 kilometers per liter. You have decided to go on a road trip, but want to take the car that gets the best gas mileage. Whose car do you take? So I'm just going to pick one. You could do the other, but I'm going to pick one, and I'm going to say that I want to know my 21 miles per gallon. That was a really bad straight line. I apologize. And I want to convert that to kilometers per liter. So the first thing I'm going to do is I'm going to take my miles and I'll convert them to kilometers. And then I can take my gallons and convert them to liters. Okay, and so now I'm going to have kilometers per liter, and I can compare with my 14 kilometers per liter. So I should have 0.621 miles per 1 kilometer. And then looking at my conversion factor sheet, I see that 1 gallon is equal to 3.79 liters. So we're going to take 1 times 1 times 21 times 1 gives me 21. We're going to take 1 times 0.621 times 3.79. So we get 21, and we're going to divide it by this answer, this number. So we take 21 divided by 2.35359. Remember, we started with 2 significant figures, so we should end with 2 significant figures, and we should get 8.9 kilometers per liter. So whose car should I take? Your car. So this is how we can use dimensional analysis in our actual lives. Now, the final one that I want to go over, just because you may see this as well with our mole to mole problems and things along those lines. When you want to convert cubic centimeters to cubic meters, we have to do things a little bit differently. So if I start with 35 cubic centimeters and I just want to go to cubic meters, okay, what I'm going to do is I can still put my numbers in, but it's not just going to be 100 cubic centimeters into a cubic meter. I have to take that 100 centimeters into a meter and cube both of those. So it's going to be significantly lower. When you do that into your calculator, you should get something along the lines of this. But you have to, if you're doing squares or cubic conversions, you need to make sure that you include the cubes in the number that you're using. So my conversion factor from centimeters to meters is 100 centimeters in 1 meter. So with that being said, I need to make sure that I include that my cubic conversion, I need to cube the 100 centimeters, and I need to cube the 1, which is going to remain the same. Now, one last thing before we leave dimensional analysis behind, and I end this video for you guys today, is going to be talking about temperature conversions. So it's important to remember that temperature conversions are going to be a little bit different than your other conversions. What I'm going to do for you is I'm going to give you essentially equations that you can use to convert from Celsius to Kelvin and Kelvin to Celsius, and from Fahrenheit to Celsius and Celsius to Fahrenheit. So the first one we're going to do is we're going to do Kelvin, and we're going to say Kelvin is K. Remember, Celsius is going to be degrees C. So we're going to say K is equal to degrees C plus 273.15. And if that's the case, if we want to do a little algebra, we're just going to subtract 273 per both sides. So Celsius is going to equal Kelvin, degrees Kelvin, minus 273.15. Now, it's a little bit more difficult with converting Fahrenheit into Celsius. And that's why generally, like, I guesstimate my Celsius to Fahrenheit conversions, just because of, if I'm in the moment, just because sometimes I can't get a calculator out. Like, I know generally, like, around 70 degrees Fahrenheit is, like, around room temperature. And that's about 20 degrees Celsius, give or take a couple degrees. So you get the idea what we're trying to generally go for. So when we convert Fahrenheit to Celsius, we have degree C is going to equal 5/9 times degree F minus 32. See how that's not fun to do conversions to. I much like my Celsius to Kelvin conversions. So or minus. I like that. It's an easy conversion. All I gotta do is subtract essentially 273. Because most of the time you're gonna get whole numbers for your temperatures. So the 0.15 you're gonna round off anyways. But generally that would be generally, I like that better. And if we're doing it from Fahrenheit, it's going to be that's what it's going to look like. 5/9 times the amount of degrees C plus 32. Not exactly the most fun thing to do. So let's go ahead and convert the 36 degrees Celsius to Kelvin. So you'll see why we all love Kelvin so much more, because we just write our equation down. And yes, you will still have to show work for your exams. Hopefully I have gone over that, but if not, please send me an email if you have any questions. So K is going to equal 36 plus 273.15. Pretty easy. All I got to add those together. So if we add together 36 plus 273.15. And remember, we're going to just for now put all of them down when we do these temperature conversions. Okay, so 309.15 degrees Kelvin. That's around 309. Next one, convert 36 degrees Celsius to Fahrenheit. No one likes to do these temperature conversions. So we're going to take 9/5 times degrees Celsius plus 32. So degrees Fahrenheit is equal to 9/5 times 36 plus 32. So we're going to take 9 divided by 5 times 36 plus 32 is going to equal 96.8 degrees Fahrenheit. So that's a really hot day in the summer. Okay, with that being said, we're going to finish up density in the next videos, which you will watch next week. And then you will also do a lab on density, virtual lab on density, and complete all of your homework. You should be able to do like 95% of your homework at this point. If you have any questions, please send me an email. I'm more than willing to do a Zoom session with you.